temperature. And each point there is a temperature, and that temperature will be some mean temperature plus minus delta T. Oh, sorry, this will not be the thing. Plus minus, that will be the measurement. And now this is true for any measurement, not only for temperature. I call it any field phi as x and time. Now time is T naught, we are measuring in the sky, and it will be a mean value delta phi, mean value phi naught plus minus delta phi. Now you tell me, from your idea of simple, if it is a random variables, means complete random fluctuation, what will be the delta phi average, means the fluctuations of this delta phi average. So some point will be higher, some point will be lower than 2.7 Kelvin. No, 2.7 Kelvin is the temperature mean phi naught. Now, if you measure every point, some point you will get. And what is the order of this delta phi? We discussed in last class. Who can tell me? What is the fluctuation?
10 to the power minus 5.
So
10 to the power minus 5.
So delta phi is more or less 10 to the power minus 5 times the mean value. So mean value is 2.7. So you'll get a different point will give you 2.7. Some point will give you 2.7, 0.0001 or 02. Some point will give you minus 0.0003, like something like that. Is it clear for everybody? Now every point will have fluctuations. Yes? So now you tell me, if I take an average of all the fluctuations, what I will get for a random field? Anybody knows from statistics? That is the definition of random field. It's not the mean value of phi naught to 2.7, but I'm taking the mean. So somewhere it is plus, somewhere it is minus, somewhere it is plus, somewhere it is minus, higher temperature, lower temperature. If I add all of them, how much I will get?
0.
Yes. Who told?
Jahan.
So this is the definition of a random field. The first moment, this is called first moment, is 0. But if you take the delta phi square average, that is called 2-point correlation function. Means you measure delta phi at one point and then another point, then you multiply and then square it. Basically that is square. Take the mod, and then if you take the average, it will not be 0. Sorry, it's square only. Any point. So that's why the second moment of any random fluctuation, it's not 0 because it's square. So that's why it is called. Now what we do, as I said last class, delta phi is a field, is anything. It can be delta rho, it can be delta t. The delta rho means it can be the fluctuation from inflation. Same, and delta t is also the fluctuation in CMB. Similar thing only. All these things, generally what we do, we go to Fourier space and we do an integral d cube x, some normalization factor 2 pi cube e to the power I kx k dot x, and then there will be a coefficient delta k. So this is the K space. So if you take the Fourier transform in the K space, so then what it means? So what does first this thing means? When you go to Fourier space, this thing means something very similar. What you have done. You have done Fourier transformation in your course, mathematical physics. Yes? Yes?
Yes, sir.
Everybody has done Fourier transformation? So suppose you have a over density or over a function, anything, delta function kind of thing, peak. If you do Fourier transformation, what you get of a delta function? Who can tell?
As constant line.
Straight line. So you get sine wave. The coefficient of the Fourier transformation is straight line, but don't you remember that this thing, delta function, if you take a Fourier transform, it is superposition of many sine wave or cos wave. Isn't it true?
Yes, sir.
Who is telling this?
Gauri Shankar, sir.
So what is the Fourier transformation? Looks like of delta function. The definition of Fourier transformation is basically nothing but any function if you take f of x, then if you take the Fourier transform, it will be like sum over k, then some e to the power I k x, k dot x, or I k x times. This is basically nothing but sine or cos, isn't it? Yeah? Basically waves and time f of k. Now sum over all the k. That means if it is a peak function in physical space-time, that means if you go to Fourier space, it is basically sum over different waves. Small wave, bigger wave, small wave, bigger. All different k's are nothing but 2 pi by lambda. So if you vary k from 0 to infinity or minus infinity to plus 0 to infinity, then you vary lambda also. So any function is nothing but superposition of different waves in the Fourier space, but with a weightage in front. There is a weight factor, and that weight factor is your fk. Yes? Yes?
Yes, sir.
So you should read the Fourier transform like that. Now, if you take this fk square in Fourier space, that gives you the kind of thing I was telling. It is related to the power. It is called the power in Fourier space. So that means if some wavelength has higher fk and some wavelength has lower fk, some wavelength has much bigger fk, then you can plot fk square versus k, and you may get something peak or something or like this, anything like that. That means in certain length, because k is basically nothing but 2 pi by lambda. So when k is fixed, if you get a peak there, that means in certain length scale, you get a peak in power, and in certain length scale again you get another peak. So in physical space you will not see that, but in linear space, so that means it is called the decomposition of anything like delta rho inflation in space time x, or delta t. Will do that right now very soon in delta t cmb. You decompose it into Fourier space and you say that in what wavelength we get maximum power. And that wavelengths are nothing but that wavelength which enters the Hubble horizon. And you will see some length there will be more power, some length will be less power, some wavelength were outside the horizon, they did not get time. So I'll show you a movie now, then you get an idea of what astronomers do in the sky. Can you hear me now?
Yes, sir.
Yes, sir.
Yeah, so now once you see, these topics are very tough. This is what people do PhD about. But this concept, if you read for a week or so, you'll get idea. And this is not only for cosmology, it is this Fourier transformation and taking their power, delta k square, it's true for all statistical physics. Okay, whenever there will be a data analysis, you have to go to Fourier space, take the mod square of that, and then that means which k or which sine waves amplitude is giving you more power. So let's see this. So this is our sky, full with star. Okay? You can see?
Yes, sir.
Yes, sir.
Full with sky. Now, looking at this, you will see it is just like a random distribution. That means if you take the fluctuations in the sky, over density and under density, and you add them, because some places are over dense, white and blacks are less dense, and that's why the galaxy has formed. So if you sum them and take the mean, what you will get?
Zero.
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 But astronomers know, but statistical physics or statistical maths, but they know that there is information hidden in this. It is not just a random fluctuation. And how they do? Let's do that. See that. So some parts are full with galaxies, cluster of galaxies. But what they're going to do, I was going to tell you, you take frequency versus how many stars are there at a given length. So this is one ruler. And so what we are going to do, we'll take different length scale, which means different wavelength, that f of k, of different 2 pi by lambda. So different lambda means different ruler, and we'll see that how, because as it is a 2-point function, delta x square. So we take this ruler and we see that in how many cases whenever I get some stars within that distance, I add it in my plot. You'll see it, what is happening. So I get on the, okay, I put it. Another bigger distance, okay, I got 1 stars. Another distance, I got 1 stars. Then you go a smaller, all the distance you cover, another star, another star, another star. And then you will see some part you are getting more. Okay, this distance I am getting more stars. Then you keep doing it in computer simulation, all distances. And finally, when you do a lot of distance, and then you see you get a peak here and here. That means, though it is a random fluctuation, there is more power in certain wavelength. And that information is very important for cosmology. And this is just an example. You don't need to know what is BAO peak now. But you got an idea now that what is happening? Yes? Or it is confusing? Any questions? Hello?
Yes, sir.
Yes, it's
Fine.
Little bit getting clear?
Yes, sir. Yes.
Yes? See, that means some distances there is more structure formation happen, and in some distances there is less, and in some distances there are peak. So then cosmology says, why I am getting a peak? Why I am getting a peak? So this idea is very important, because if you just take delta phi average, you will get 0. But you have to do the 2-point correlation function. So this is your homework now. Today you read 2-point correlation function from statistics or in cosmology, anything. You get an idea why 2-point correlation function or delta phi square is most important. Okay. I have told you many simplified things, because actually it is delta phi x1 times delta phi x2. As you can see, I am taking 2 points and then I multiply and average it out. Okay. So that tells me some distances has more growth in clustering. So now to answer your question, in last class, as I was telling, suppose this is our horizon, and from here we take a very large distance like that, a ruler, and if I rotate it in different direction, we take a ruler like this. This is the same distance here, or diameter distance, a 2-point correlation function of this distance. So which is of the order of Hubble horizon. Then you will see the power or the delta k square in that distance for k very small. K small means lambda is very large, is small. That means if you get a peak, you will see that as you go to higher k, the peak increases. Okay, so this is called pk versus k. Pk is basically nothing but delta k square. You will see more power. Now, to answer your question, suppose you are saying that okay, there is less galaxies. It is in physical space, delta x. There are galaxies here also. But now suppose there is an observer here, another universe, alien. He draws his line, and this distance is a very small distance for him. Say observer is here in the center. So now he takes his ruler like this. For him, this ruler lambda will be much smaller than this ruler, our universe, lambda us, our universe. This is lambda them. So when they plot, they will get some power also, but they might not see the same power what we are seeing, because our distance lambda is different, because to get a 2-point correlation function between edges of the universe, your lambda has to be very large. So what it means is they will also see some fluctuations, but the fluctuations they will see delta x square when they split it in different sine wave, sine or e to the power ikx. Their k will be different than our k. So their amplitude will be different than our amplitude because it is not the physical fluctuation you see. It is the Fourier transform of that. That means you are decomposing it is in many waves. And one such wave will be their distance. So that's the whole idea. So you cannot just say what you are asking last class, that said there is still galaxies there. Yes, there. But how much in 2-point correlation function is the main thing. So once they do 2-point correlation function, they will also see. But if they come to a very large distance of their horizon, they will also see that in this distance, they are finding very less. The corresponding wavelength lambda, the corresponding power in lambda, sine is less. So it is a little bit intuitive. You have to do a little bit statistical physics to understand it. So my point is you do the homework, read it very nicely, and you get an idea, see some YouTube video. And I'm going to show you 2-3 more video today. You'll get more idea. So now, this video is done. Can you see this?
Yes, sir.
What is this? Tell me, what is this?
CMB.
Huh?
CMB.
This is the picture of the universe when hydrogen atoms was formed. So CMB, cosmic microwave background. What is the mean temperature?
2.73.
2.7. But the reds one a little bit higher and blue one is little bit lower. But the fluctuation is of the order of how much? 10 to the power?
-5.
-5. This is the map our NASA has got and European Space Agency has got for 2 big experiments. One is called WMAP experiment, another is called Planck satellite. Both are satellite. They were launched from European Space Telescope Agency, Space Agency, Guyana. And the Planck satellite took this magical picture. So universe looks like this. When universe was just 380,000 years old, which is almost baby compared to our age of the universe, 14 billion years. Is it clear?
Yes, sir.
Universe was a hot gas. That also kind of proves that Big Bang idea is right, that we are in a hot plasma. There was no galaxy, no stars, nothing. These temperatures are nothing but the temperature of the gas. And what were main component of the universe that time, which was playing these dynamics? That will be explained in this video. So just looking at this map, you cannot tell anything. But when you do statistics, you'll be amazed to see from this just simple map, cosmologist has been able to tell universe is 14 billion years old. Cosmologist has been able to tell that 0.3 or 0.26 is the dark matter, means 26% is dark matter. They have been able to tell 4% is visible matter and 70% is dark energy. More than that, they have also measured the value of H naught, the Hubble expansion rate, looking at this map. So there is so much hidden information in this simple map, but looking at it, you will see just a colored map of random fluctuation, isn't it? Yes?
Yes, sir.
For that, you need to know all the statistics. So that's why it is not so easy to tell you this story, because people take one semester course to understand the statistics of CMB. But you can read the 2-point correlation function. But let me go through this video.
Is what this looks like, when we just look at it. It looks like a random noise map. But if we take a 2-dimensional Fourier transform of this 2-dimensional map, this is a map of the 2-dimensional surface of the sky. If we take a Fourier transform of this map and then plot the square of the Fourier amplitudes as a function of wave number, we find that there is a power spectrum that has very well-defined and interesting features. So here we go from left to right. This is the wave number, and the wavelength of each Fourier mode is indicated on the top. So these are 1 degree wavelength. These are 0.2 degrees, 0.1 degrees, etc. And off to the left is 90 degrees, L equals 2 to the quadrupole. Strictly speaking, since this is a spherical two-dimensional surface rather than a flat two-dimensional surface, we are doing a spherical harmonic transform, which is the spherical surface analog of a Fourier transform. And so the wave number is a multiple moment, L over here.
Okay, so the basic idea is same what I was telling, that you go in the Fourier space and power it, square it, and square it of that map which I shown you with some computer, and you get this amazing thing. And you see that some wavelengths have more power, means more fluctuation. That means more over density and under density. Fluctuation is square, no? So even if it is under density, it will get square, you know? So it basically measure of how much deviation you are doing from the mean. Whether upper or lower doesn't matter, because both negative square will go in as high, because square is always positive. Is it clear? Yes?
Yes, sir.
So that means it is a measure or how much over density or under density you have in temperature or in that density. Basically, they are related, proportional. If you have over density in gravitational matter, they will have over density in temperature, because you have clumped more matter, so their energy will be high. So now each peak here tells you very deep thing about some cosmology, which I will not be able to do it, but we'll show you a video, because that's what, if somebody starts doing PhD in cosmology, that is the first reading course people has to take on CMB, that what this peak mean, what the second peak mean, what's the third peak mean. You will see the first peak will give you the age of the CMB and how much photon has traveled. Okay, I'll show you the video, you will understand it. Second peak and third peak will give you dark matter and other thing. First peak can also give you the rate, Hubble expansion rate. So there are information, you don't need to know how it works, then otherwise you will be a PhD student now already in cosmology. You don't need, but now let me play the video.
So it goes from 2, the quadrupole at the left, all the way out to several thousand on the right.
So basically 1 degree, as you go to the right side, the degrees are nothing but your wavelength only. How? Because I have already told you that for spherical thing, so this is suppose the CMB sky, so it is a sphere. Then you take, this is us. So this is the degree. So if you take some patch where you get over density more, so suppose this is a lambda, 1 lambda. You can take another bigger patch, like different length scale, because as I say that Fourier transform is nothing but superposition of different sine wave or cos wave, sine kx. So here, if you take the over dense, some part is over dense, some part is under dense, some part is over dense, some part is under dense, some part is over dense, some part is under dense, like that. It cannot be alternate, but it's a random field and it's a sphere. So here you can see that 1 degree, this distance we know, dA, it is called angular diameter distance. So if you know this distance, say r, so angle is nothing but r divided by dA. That is called the angle, angular scale. So it is also like higher angle means higher distance. If you go even more higher angle, 90 degree, that means it's a distance like this. Is it clear? Yes? So that means you are looking for a ruler stick, 2-point correlation function of this distance, which the previous video I have shown. So now let us go back. And for this one, you will get an understanding that what is happening. Just 1 second, where is the video? Yeah.
And If you look, this
Just one. You can see the video.
power spectrum peaks at L of roughly 200, which corresponds to 1 degree in the sky.
Now let us, I will go to this. So this is what I want to say.
That shows you.
Okay. So first let us see, because in the universe, there are dark matter, there are, that time before CMB, there are electrons and proton neutrons were bound together. Okay, they are called baryon photon plasma. That is the right top. The first one is dark matter, and the below corner below is neutrino. Okay, you don't need to know the right bottom. So if you take over density and if you let it evolve in Hubble universe, it will spread like a wave, because over density till the CMB was happening. So let's see the video, you will see what is happening.
What the sound horizon is. But before I do so, I'm going to tell you what you're looking at. So we have a universe that is very smooth. And if we think about the early universe, we had a system that had a very nearly homogeneous density. And it consisted of dark matter, actually I can't see this right now. But dark matter, it consisted of neutrinos, and it also consisted of photons and baryons. Now suppose that if on top of this smooth distribution of stuff, dark matter, neutrinos, photons, and baryons, we introduced a delta function, or narrow peak, density peak of dark matter, baryons, photons, and neutrinos. So suppose that in the early universe, instead of having a perfectly smooth, homogeneous early universe, we had one point in the universe where the density of all the components of matter, dark matter, neutrinos, photons, and baryons, was higher. Well, you can imagine that what happens is that the baryons and photons, which form a type coupled plasma, because the early universe consists of ionized electrons and ionized hydrogen atoms, and the photons scatter from the electrons, they form a plasma. And if we have a high density region, that high density region is also going to be at high pressure. And that high pressure region will then expand as a blast wave out into the surrounding medium. So this movie is going to show you the expansion of that blast wave as it goes out into the expanding medium in the photons and in the dark matter. Sorry, in the photons and the baryons. The dark matter interacts with everything else only gravitationally. And so it's going to be spread out slowly, given that the gravitational field of the photons and baryons is expanding outward. So it's going to be attracted more slowly to this expanding shock wave of baryons and photons. And the neutrinos, though, are collisionless and move at the speed of light, so they simply diffuse out with time. So here is the movie. So here is the dark matter. It is spreading out slowly. Here is the shock wave in the photons and in the baryons. And I'm going to stop the movie 380,000 years after the Big Bang. So what we've seen is that from the Big Bang, time equals 0, until 380,000 years after the Big Bang, what's happened is that this shock wave in the baryons and photons has expanded out to the sound horizon. So 380,000 years times the speed of sound.
So let me explain you a little bit more. So the top one left is dark matter. What is the pressure of dark matter? W. We have talked about it. Who can tell?
Minus
W is equal to P by rho. What is the pressure for dark matter?
0.
For any matter, what is the W?
0.
Do you remember, all of you, that W equals to 0 for matter-dominated universe?
Yes,
W-
sir.
Yes. So my dark energy, it is -1. P equals to minus rho. And for radiation, pressure is how much? Ravi, you don't tell other people. Yeah.
1/3 rho.
1/3 rho. So now you tell me, if something has a pressure and if you let it evolve, that will expand more than which has no pressure, isn't it? Like a balloon. If you puncture the gas, so see, why dark matter is also spreading out? Because the universe is expanding. But which has an outward pressure, that will expand even more, isn't it?
Yes, sir.
That's why you can see the radius. Now the neutron and proton does not have pressure because they are like matter. But the problem is neutron and proton are strongly interacting with what? Before CMB, who can tell me? Scattering, I have told you. With neutron and proton means basically atoms, okay? Nucleus. Atom is interacting with what? Ionizing with what?
Photons.
Photons. Basically, photons are every time colliding with atoms and making you ionize. That's why it is a plasma. Yes? So, you cannot distinguish these atoms is called baryon in cosmology. So, baryons and photons are together. They are called baryon photon fluid. Now, as photon has a pressure, suppose you are together with one of your friends, girlfriend or boyfriend or best friend, doesn't matter. Now, if that person has some quality, he wants to go to movie a lot, you have to go to movie at least sometimes with him or her, isn't it? Yes? Yes? Are you there?
Yes, sir.
So in the same way, photons are interacting with baryon. Photon is like, hey, I have a pressure, but better you also follow me. So that's why baryon and photon both behave like a combined fluid till the CMB. After cosmic microwave background happens, photons are free and atoms are like matter. So till this distance, they have photon and baryon traveled some distance like a pressure fluid, like a radiation. But after that, photon will be freely moving to us, and baryons or atoms are not interacting anymore after CMB, and they will start following the dark matter behavior because they have become pressureless after this. So now see this length, this ring of baryons. It is like a wave. Suppose you are in Puri Sea Beach. When the waves are coming, if you know its velocity and how much time the waves are coming, you will see it will get a peak near the beach and then it falls off and breaks. Yes?
Yes, sir.
And that peak is moving as the waves are coming. In the same way, the falls off happens, a wave falls off, a wave does not grow anymore after the CMB gets released because that time photon and baryon separate. But till this distance of ring is nothing but a delta function in spherical polar coordinate, delta r minus r naught. R naught is the variance. This r naught is nothing but the radius of the distance, how much photon has traveled, and that I have been telling you, it is 1 degree from the horizon problem. You remember? Yes? Yes? That how much distance photon can travel, a diameter, which you subtract today in our angle, that angle I just shown you, that is how much? From Big Bang to the time of CMB, how much distance it is in angular scale?
1 degree.
1 degree. We expect that much distance would be horizon size, and within that should be same temperature. And we have discussed all the horizon problem and inflation. So this distance, what baryon photon has traveled, let me show you again. That
And baryons.
yeah, let's watch it.
Now, suppose that if on top of this smooth distribution of stuff, dark matter, neutrinos, photons, and baryons, we introduced a delta function.
Why do we introduce a delta function? Because delta function is just a peak in the density fluctuation. So it's just a nice modeling that you have a smooth density plus delta function in different points. Okay, that's what, and the amplitude of that delta function is how much? Who can tell me intuitively? How much over density will be amplitude given by inflation? How much? Very low. Who can tell? The delta functions are not infinity. It's just a peak, but its amplitude of how much?
10 to the power minus 5.
Yes. That is what the over density, isn't it? Are you all getting it? Because we cannot create more over density. Inflation has told us that how much over density we have. 10 to the power minus 5. Yes?
Yes, sir.
And that we are showing what happens to that over density.
Or, narrow peak, density peak of dark matter, baryons, photons, and neutrinos. So suppose that in the early universe, instead of having a perfectly smooth, homogeneous early universe, we had one point in the universe where the density of all the components of matter, dark matter, neutrinos, photons, and baryons, was higher. Well, you can imagine that what happens is that the baryons and photons, which form a tightly coupled plasma because the early universe consists of ionized electrons and ionized hydrogen atoms, and the photons scatter from the electrons, they form a plasma. And if we have a high density region, that high density region is also going to be at high pressure. And that high pressure region will then expand as a blast wave out into the surrounding medium. So this movie is going to show you the expansion of that blast wave as it goes out into the expanding medium in the photons and in the dark matter. Sorry, in the photons and the baryons. The dark matter interacts with everything else only gravitationally. And so it's going to be spread out slowly, given that the gravitational field of the photons and baryons is expanding outward. So it's going to be attracted more slowly to this expanding shock wave of baryons and photons. And the neutrinos, though, are collisionless and move at the speed of light, so they simply diffuse out with time.
Neutrinos also.
So here is...
They're like massless almost. So neutrino also moves very fast.
So here is the dark matter. It is spreading out slowly. Here is the shock wave in the photons and in the baryons. And I'm going to stop the movie 380,000 years after the big...
That is the time when CMB got released.
So what we've seen is that from the Big Bang, time equals 0, until 380,000 years after the Big Bang, what's happened is that this shock wave in the baryons and photons has expanded out to the sound horizon. So 380,000 years times the speed of sound. And in this early universe, the energy density is dominated by the photons. So the speed of sound is roughly 1 divided by the square root of 3 times the speed of light. So it's 1 over the square root of 3 of the light horizon. So that is this spherical overdensity over here. The dark matter has expanded out a little bit, but more smoothly because it's not coupled to everything else except through gravity. And the neutrinos have diffused out. So this is how this overdensity would appear at the surface of last scatter. Now what happens afterwards is that the photons then free stream. So suppose we looked out into the sky and somewhere in the early universe there was this overdensity and then had expanded by this sound horizon. We would then see this spherical overdensity. But when you then take the Fourier transform, it winds up looking like this. So if I take a Fourier transform of this spherical shell, the spherical blast wave, the spherical blast wave is fairly sharp in configuration space, but in Fourier space, it has ringing. And the spacing in Fourier space of these spherical shells, the Fourier transform of the spherical shells, the peaks that show up in the ringing have wave numbers that are inversely proportional to the sound horizon. So this is the Fourier transform of that blast wave. This is, in some sense, the Green's function for that blast wave that has a size of the sound horizon at the surface of last scatter. Now, strictly speaking, the early universe does not have just one overdense region. Strictly speaking, the universe has some spectrum of fluctuations, but the Green's function for that spectrum fluctuation still looks like this. So when we look at the...
So this map, when you take Fourier transform, the map I showed you, you get this. And this first peak is nothing but around, you can see the angular scale, angle is 1 degree, 1.04 something. So this is nothing but corresponds to the horizon size of the universe. That means how much photon along with the atoms has traveled because they are coupled. And there you see the peak. And as atoms were hidden there also, so now if we look in the sky, today, I will go back to the first video again, then you will be able to see what I was telling, that Baryon Acoustic Oscillations. This is called the Baryon Acoustic Oscillation. You will see if atoms, so if the waves are coming, and waves, you see a little bit peak at a distance of that 1 degree. That means that waves has what? Waves has atoms also. So they also form galaxy later. So at that diameter distance, if you take a 2-point correlation function, you should see a peak. And also in the center, because center में तो over density high, it is there over density, but again the over density is in the where the wave has traveled. So now let me play the video, then you will see what I was meaning by Baryon acoustic oscillation. Okay, so this is suppose a baryon photon coupled fluid. Okay, now let them expand, and here CMB happens. That means you see there are 2 peaks. One is in the center, another is at a radius r. Is it clear for everybody?
Yes, sir.
Yes, sir. So now, if it is yes, sir, so now you'll see in the center there will be more atoms, and of course around this radius r there is a peak in density, so there will be more atoms. Yes?
Yes.
Yes,
So if
sir.
there are more atoms, later they will form galaxy later, and this is happening everywhere in the universe, not in one point. So see this video. So this peak was there every point, that is a fluctuation, 10 to the power minus 5. And then every point will have a wave interface like that. But see, it is like a mountain valley. Some part is high in density. You see? So this is the snapshot of early universe. Now, this ring area and the central area will have more over density today because they have more atoms. Now, if you look into very powerful telescope in the sky, you see the central area has more density. You can see that, no? The more clumpy center area. Can you see?
Yes, sir.
Yes, that is the starting point of over density. But if you really see, can you see that ring around that center? Can you look into it? It is faded, but if you have an eye of a statistician, you will see there is a ring also. Take a radius, that picture, and can you see the ring little bit forming?
Yes, sir.
And the rings are overlapping. So now I showed you this ring, that's why you are seeing ring. But if I show this picture to somebody else in a street, he will say it is a random fluctuation. But as you know the physics, you know that it is not random fluctuation. So you can see the ring, around that every blob there is a ring of that baryon waves. Yes, photon waves. Yes, yeah. That size of the ring is around that time it was 1 degree CMB sky. But now if you measure in the sky, the size has changed because the universe has more expand, but you will still get a peak. So see what is happening. So this is the center of galactic cluster. But we'll now do the statistics. We'll take different ruler and we see where we see more structures, more density. And then we do the same thing. This is what actually we are doing Fourier transformation. Okay? Different wavelengths and putting their power. Every time I count 1, I just put it. If I count once again in the same wavelength, I double it. See? Double it. That means where then slowly all wavelengths will get multiple points because it's filled in the sky, but some of them will get more peak. So now you see the first peak is the first over density, and the second peak is the how much the baryon and photon has traveled. Clear? Yes?
Yes, sir. Yes.
So you are getting some intuitive feeling. Now you see, we look into this Hubble Space Telescope or IIA is planning TMT. What they will do is they will go and measure billions and billions of stars and then do this frequency plot. And they will see where I see the peak. And then they will go back in early universe. Why I am seeing the peak in this 1 degree? They will match it and they will say, oh, that is the speed of the photon baryon fluid. You know, Mark Kaminkowski, he is the person who was speaking. He is like the best cosmologist of present time. America, Johns Hopkins University. So, but he is a very good speaker. That way he could explain it. So I work with him a little bit nowadays. So he told you that the speed is actually not c. It is actually a little bit less than c, 1 by square root of 3 times c. Why the speed is less? Because there is a competition. Light wants to bring it to the c, but whereas the baryons are heavy. So together they compromise to 1 by square root of 3 times c. That physics can be understood by some later equations, which we will not be able to do, but those who want to be interested, I can give you reference. Suppose baryons means proton, neutron, and electron are combined with photon. Photon is moving in the speed of light, whereas atoms has less speed because they have mass. And how combined fluids have the speed that is 1 by square root 3c. Okay, because combined fluid has to be a little bit less velocity. Is that clear? Because if you are pulling a heavy thing, you will slow down, isn't it? Yes?
Yes.
Yes, sir.
Okay, so now it is the time to turn on the video. Okay, so I have been doing a lot of bok. So then I'll take a break. Yes. So is it getting little intuitive, clear that what is Fourier transform and what we do? Yes? Yes? Different frequency, different wavelengths. Yes, clear. So any questions you have? So Srivardhani, I see, we saw you first time today. Okay, you came and then you again went, but at least we saw you. Okay, very good. Yes. Avinash, are you there? Oh, okay, very nice. So you are all doing good. Don't go out next 10-15 days, okay? You are not going out, no? Okay, very good. So if you don't go out now, you'll be able to go out nicely later, okay? So you have to constrain your tendency to go out, okay? And take some good protein food, do some stretching because you need to build your immunity, isn't it? Huh? Okay. Are you taking vitamin C more, zinc, or no? देखा जाएंगे जब हो जाएगा तो देखेंगे. Okay, so like that. Okay, very nice, good. So now you know when we say there is a peak in the CMB, you got some idea why it is the first peak. It is this peak. Like second and third peak, we cannot go that much deeper today. But looking at the peak, we have done magic, and that has given cosmology a very powerful tools to talk about early universe. Okay, so now let us go to the next part. We can switch off the video. So now it will be a little easier. This concept was a little tough. So now the photon temperature, photon is actually a black body radiation, what we see the CMB photon. So what is the spectrum of a black body radiation? Anybody can tell with the frequency. If you plot the intensity, you'll get like this, or you get a peak, something. Anybody has done black body radiation?
Yes.
Get a peak. So what does peak means? peak is somewhere, and you will do your homework, find out the peak, because next class we will need that as a function of frequency. At what frequency you can get the peak. From statistical mechanics book, you can find the peak. I knew. You'll see it will be a function of function of nu frequency. Yes, you remember? Yes, it is a complicated function. Yes.
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 Maxwell-Boltzmann distribution kind of thing. Yes. No, it is. If it is a non-relativistic matter, it will be Maxwell-Boltzmann. Here you will see it is a. It is called which distribution?
Planck's distribution.
Planck's distribution, which can be derived from statistical physics, statistical mechanics course. You remember that starting from Bose-Einstein distribution function, you can actually derive Planck's distribution. Anybody has done it in their StatMech course or no? Yes,
Yes,
or no?
sir.
Yes? How many know? Even if you forgot, it's okay, but you have done it?
Yes, sir. The last semester we did.
Last semester only did it, and you have forgotten, that's also okay. Okay, so tomorrow in next class we are going to do that. Okay, so what does it mean? Can somebody tell that if there is a peak in some frequency, that means what? That means in a room of Blackbody distribution, you see, new different means basically temperature is also different, isn't it?
Yes, sir.
Yes, sir.
So that means even if there is a thermal equilibrium of photon, still some photon will be at lower temperature, some photon will be at higher temperature. Yes?
Yes, sir.
So there is a distribution in T. Nu is basically nothing but T. Higher T, this is lower T. But you will see there are so many numbers of photon. Again, you do the similar thing. Every time you find a photon with a temperature T, you plot them. And again, you find temperature, you take another photon, its temperature here, you plot them. And again, you find another photon, okay, a little bit higher temperature, you add. And then you find another photon of the same temperature. Then you find another photon here. Then you find another photon here, another photon here, another photon here, here. As a karte, the same thing you do, frequency plot. And that means you get a peak that means the number density of photon is maximum at a wavelength nu naught. This is nu naught. Yes, that means number density is peaked at a temperature T naught, but that doesn't mean that there is no higher temperature or high energy photon in the room. Is it clear? Yes?
Yes.
Yes, sir.
The distribution function. So now, CMB, we'll use this knowledge. So CMB happens when, cosmic microwave background, that this is your proton and neutron, and this is your electron moving. But every time it was trying to combine, a photon come and knock it out. That is called scattering. This is the radius of the neutron. And that's what it's called plasma. And this plasma is called baryon photon plasma. Baryon is nothing but neutron, proton, and electron. In cosmology, together called baryon. And photon is photon. Photon has velocity and pressure. W is 1/3. Originally, this thing has no pressure. But when you make them together, they become one entity. As I told you, they have become a pressure fluid, baryon photon. And its pressure and its velocity, of course, become less than c because photon has to pull the heavy atoms. And velocity actually becomes this, combined velocity. Combined velocity. 1 by square root of 3. I have to. Now, what is the energy of this E1 in electron volt? Who can tell me? First orbit energy of the electron is how much?
511
No,
kilo.
the electron energy of the orbit of a hydrogen atom.
Oh, that one. 13.6
13.6.
13.6 what?
electron volts.
Electron volt.
You know that, everybody? Yes?
Yes, sir.
Now, if I have a photon energy, E equals to H nu, which is greater than 13.6 electron volt. So universe photon temperature is actually falling by T gamma naught at high temperature by A. I have not proved it, we'll prove it next class, but I told you that as universe expand, like a gas, when it expands, its temperature falls. Isn't it? Yes? Yes?
Yes, sir.
In a thermodynamic gas, if you expand the gas volume, will temperature drop or increase? Huh?
Drop.
Will drop because this is the whole idea of thermodynamics. If you have a box, temperature is nothing but what? The kinetic energy getting rebound from the wall, isn't it? That is the kinetic theory of gases, isn't it?
Yes.
If you now expand the volume, then definitely the number density of photon colliding will decrease. Yes?
Yes, sir.
And then the total momentum transfer in a unit area will decrease. And that's why the temperature will decrease. Same way in cosmology, it just decreases scale factor. Very interestingly, we'll prove it in next class. So photon becomes lower and lower. So at early universe, sorry. Early universe, photon temperature was higher than 13.6 electron volt or lower than 13.6 electron? Who can tell me? Very early, before CMB.
It should be higher.
Higher than.
Higher means it is very, 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 very higher, okay? Photon temperature was of the order of GeV or even more than. It can be even 10 to the power 9 or 10 GeV. GeV means again 10 to the power 9. So huge temperature after inflation ends. And that temperature was created from latent heat of what? We discussed last class. See, after inflation, universe become empty. Yes? You remember that rapid expansion in the beginning, universe, everything was thrown outside the horizon. Isn't it?
Yes, sir.
What remains inside is nothing but the energy of the inflation. Some unknown vacuum energy. We'll do it in the 2 class later. This inflation is unknown. We don't know. We can call it whatever, the primordial energy. Some people call it God. So we don't know. Some people call it nature. It's nothing. We have no idea. Even Stephen Hawking doesn't know what it is. But we give it a name, inflation. Sometimes we parameterize it with some field energy. But we don't know where this field energy comes. Suddenly that at the end of when everything was outside, empty, then this emptiness, latent heat of the emptiness creates all plasma, all particles, E minus, quark, Q plus, antiquark, neutrino, electron, muon, tau, all particle of standard model was created at the end, and they were in a very hot temperature, T hot plasma, very hot. That is called Big Bang. Big Bang is not the initial expansion. Initial expansion, what happened, nobody knows. Okay, Big Bang means, and this also happens. This inflation ends around 10 to the power minus 27 seconds. So this happens 10 to the power minus 26 seconds. So you can see that it is much less than even 1 second. Now this temperature is very high, 10 to the power 10 GeV. Of course, the temperature of photon. So now photon temperature starts cooling down as 1 by A. Cool down, cool down, cool down. And when will the photon will get released? When the plasma behavior will be over? When the CMB will be released? When the first atom will be formed? At what temperature? When the energy of the photon reaches around how much?
13.
Huh?
13.8.
13.6 electron volt. Because if it goes below, then it will not have enough energy to knock out the electron from the orbit. Because your energy has to be around 13.6 electron volt or higher. Isn't it?
Yes, sir.
But we see actually from CMB experiment that this happened actually much lower temperature, 0.3 electron volt. Who can give me the answer? Why? The answer is a little bit hidden in the previous thing I just told about the last slide, the Planck distribution.
So even at that temperature, there will be some photons which are moving at
Very nice. Who is speaking this?
Avinash.
Avinash. So when I say the temperature of the photon is 0.3 electron volt, 0.3 electron, that means, when I say 0.3 electron volt, that means the peak of the Planck is at 0.3 electron volt. Yes? But there are photons at higher temperature, and the photon density is so high, so even in 13.6 electron volt, there will be some distribution. So if you plot it, there will be some energy of 13.6 electron volt photon. Is it clear?
Yes, sir.
Because it's a distribution. But now the number density of photon is much, much higher than in baryons. Baryons means atoms. In fact, photon number density is in cosmology 10 to the power 9 times in baryons. That means even if a tiny fraction of photon has 13.6 electron volt, their number density is so high because 10 to the power 9 times the atom number. So even if here you have low number density, because this is nothing but number density, as I already told you, number density at different temperature. That is what basically related to the intensity. And that's why you use Bose-Einstein's theory, because Bose-Einstein talked about number density, and then from there you go to intensity. It's basically number density. You can see that at some temperature, it is 0.3, it is peaked, but there will be enough photon. And as the number density of photon is very high, 10 to the power 9 times baryon, even if here you drop by say 10 to the power minus 5 factor, say it's a very tail of the distribution, still you get 10 to the power minus 5 times 10 to the power 9, 10 to the power 4 times photon at 13.6 electron volt. So that's why you need to do a proper computer simulation, and that was done by cosmologists using Meghnad-Saha equation. I'll not go into the detail. Meghnad-Saha equation lagake they calculated. So it is not a straightforward. You have to see what is the ionization fraction and how much energy density in each photon here. Aisa karke, then they come up with TCMB is 0.3 electron volt. So it means the mean temperature of the photon is this 0.3, or the peak is at 0.3 electron volt, but there is enough photon at higher temperature to ionize the electron. But when you go below this, then effectively you cannot ionize. That is the computer differential equation solved. Not a very straightforward calculation. 10 pages of calculation of ionization equation, fraction of ionization by Saha. This is an Indian scientist. They used Indian scientist equation to find this. So CMB happens at much less temperature than 13.6 electron volt. Is it clear?
Yes, sir.
Yes, sir.
So this gives you an idea about. So see, in physics, there are two ways to do physics. One is you go to class, you solve all the equations, you know. But are you able to see that every equation has some physical significance, isn't it? Yes?
Yes, sir.
Today I told you that you all know about Planck distribution, but what does Planck distribution tell? That you see, oh, that means there are many temperature, but one there is a peak. Okay, like that. Okay, so cosmology mein you get everything. GR, we use Friedman equation, you get special relativity, you get the idea of horizon, that beyond that moving much faster than the speed of light, space is moving, so you cannot communicate. Then in cosmology, slowly you are coming into the acoustics where it's Fourier transform. And then in cosmology, we have now come to a point where we are moving into the thermodynamics, Planck distribution. So next class will be thermodynamics, that how temperature falls as 1 by A, and many more things. How can you calculate the photon temperature, average, all will be studied. So if you can go back to your StatMech course, go that how you do the average in momentum. You remember, if to do the average, you have to multiply with the distribution function and do an integral. Remember? Yes? How many of you remember the zeta function you got in StatMech? Yes? Go back there, read that. So StatMech will be very important. And today also we did a little bit of statistics of 2-point correlation function, mean. And then in cosmology, we also have, I have not derived, let's see if I get time, that 10 to the power minus 5, how can I derive from quantum mechanics? So you have to be good in quantum mechanics, you have to be good in StatMech, you have to be good in GR, you have to be good in statistics to understand the universe. So universe is an amalgamation of physics, statistics, different part of physics, classical mechanics. Last two class we'll be using classical mechanics, okay. And StatMech, then statistics, and then chemistry also, and of course math. Okay, so that is how cosmology. So the concepts we are going through is very not so easy. As you know, you are already confused about that horizon crossing. You have to read about it, think about it. You can ask me one day after I finish the course if you need some explanation. And you can ask me about other things in cosmology if you don't even understand. But the ideas are very, very subtle. But the mathematics are not so deep. You can, simple arithmetic we are doing, okay? Next class, we'll be doing little integral zeta function, okay? Any question now? So you can recap till now, whatever you remember, that whatever topic we have discussed, even if you don't remember, but at least you remember the topic. Now I ask all of you to speak. I have been speaking a lot. Then I get golame, throat thing, you know. Yes. So who will speak? What are the things till now? 6 class done, 6 or 7 class done. What are the things we have done? Tell. Anything you remember, just shoot. Just the topics. Yes, start.
We have discussed about FRW metric. Then FRW metric.
FRW metric, very nice. That how to get metric with the scale factor 80. Yes?
Yes, sir.
Okay, now anything else? Everybody should speak. Bolo. Horizon problem and flatness problem. And what is the solution to that? Both. We have done the solution. Inflation is nothing but similar to what?
dark energy.
Dark
dominate.
energy expansion. Yeah.
Dark energy expansion, but at a much higher scale, higher energy level. But the physics is very similar. How the scale factor expand? You know how the space expand? What is the formula for dark energy or inflation?
Exponential.
It is an exponential. When you are exponentially expanding e to the power lambda t, whereas light is going as linear ct. That's why space crosses the speed of light. And that's why your Hubble horizon is the velocity of light, but space goes much beyond. That's why your Hubble horizon becomes smaller, but the space horizon is much bigger. That's why the Hubble horizon se sab kuch bahar chala jata hai. Everything goes out of Hubble horizon. Yes, we did that. And when do they enter our universe? Horizon, Hubble horizon? Because if they all the time remain outside our horizon, nothing will not see anything. They have to enter, no? Yes. Which dominated era they enter? Who will tell?
So different scale enter at different eras, like
Yes, but more or less
in matter dominated era.
in radiation, little bit less, and in matter dominated era. Yes.
Yes, sir.
But again, in dark energy dominated era, what is happening? The scales and the fluctuations, what they are going to do?
Leave the house.
So luckily we are in a time where dark energy just started and things have started moving out, but most of the things are still inside. Okay? Only the nearby horizon things are moving out. But if we have come here 4 billion years later, 5 billion years later, what would have we seen?
Just
That
our surroundings, Milky Way.
only Milky Way, nothing else. And you will see that is the reality, that is the universe. And the ancient people who have done all this Hubble horizon, all these billions of Hubble Space Telescope statistics, data with billions of galaxies, they say like they are completely weird. Okay? So see, the knowledge has relevance at different time. Okay? You cannot, every time the knowledge we have is the most useful. And then later, but you cannot discard at the fire age, stone age, they didn't have electricity, but just rubbing the stone, the fire they got, it's very similar to our electricity today, isn't it? Yeah? Yes? So that's what it is. But now it is very important that we are in a very nice time of doing space physics. Why? Because many things we don't know. So what are the things we don't know? Can you tell? We know they exist, but we don't know what they are. What are they?
Dark energy.
Dark energy. How much
Dark matter.
percentage it is of the, how much energy budget?
70%.
70.
Huh?
70%.
70% we don't understand. And next, which
Dark
one?
matter.
Huh?
Dark matter.
Dark matter. How much percentage?
26.
26. So remaining 4%, we try to understand visible universe. So if you think you are knowledgeable, you should remember about dark matter and dark energy. Okay. If you think your all opinions are right, then you'll know that 96% of the universe we don't know. So that's why the more we know, the boundary of knowing expands to more unknown, and more we realize that we don't know more. But for that, you have to know more, that you don't know anything. Yes? Yes? So that's why the more knowledgeable you become in anything, the more humble you should be. Okay? That's the nature wants you to be, because nature can reveal more that there is so many things you know. The problem is half knowledge. Those who does not know anything, they also know I don't know. Okay? And there are people who know a lot of things, they also know there is no, I don't know. But if you know a little bit, then it's a false idea, I know a lot. So medium baked pizza is not good. You have to be full baked. Yes? You cannot keep it in the freeze, which is non-baked. Neither you can eat it. Yes? Very nice. Okay. So anything else? What else we did? Many things we did actually in 6th class.
Friedman equations.
Friedman equation. How many Friedman equation? Independent?
2.
2. And from the 2 equation, we have derived a third equation. Yes?
Yes.
What is that called?
Continuity equation.
Continuity equation. You have all done the homework. Yes? And we have used the continuity equation to solve how scale factor expands, how density changes in different matter dominated, radiation dominated, and dark energy dominated. Yes?
Yes.
What else? What else we have done? Who tell? Anything you remember? Or this is pretty much it, nothing else.
How the structures form.
We have not done yet totally, but we have shown that for making the stars, we need what? Who can tell? Not Ravi, somebody else. Making the structure in the universe, you need a initial,
Fluctuations.
because if you have a total homogeneous universe given by Lord of the universe or universe himself, then you will not be able to create galaxy. Because why? I have discussed it. Why?
It will be uniform, so
Uniform. So each point the force will
cancel out.
cancel. So there will be no net gravitational attraction in any point. So you cannot pull things. Yes? Very nice. And so next two class will be more on more on thermodynamics. And then the last 2-3 class will be more on, we'll discuss how this 10 to the power minus 5 become more and more. And at some point they collapse into galaxy. To collapse into galaxy, we will show you the delta has to come at least of the order of 1. So it has to increase by how many factor? 10 to the power?
By
10 to the power 5. That is called the theory of spherical collapse. So you have to increase from 10 to the power minus 5 to 10 to the power 5. How universe did that? Collapse means what? Collapse means when gravity is so high, then whole thing collapses and then star forms by balancing it. Not star, the halo form by balance. It is called virialization. Okay, you don't need to know all this detail, but they become a stable spherical structure of halo, dark matter halo with stars inside it. We call it galaxy cluster. Okay. So that's it. Anything else we did today? In today's class, we did something else, no? Fourier transformation, yes?
Yes, sir.
What did you learn today from Fourier transformation? That
2-point correlation function.
2-point correlation. Read about it, okay? And this 2-point correlation function basically keeps the hidden information of the statistics going on, the physics going on behind the random fluctuation. But if you have an eye of a statistician, looking at it after I told you, you can see the ring structure today. Yes? Yes?
Yes.
But if I didn't tell you, when first time I showed you the video, did you see the ring structure?
No, sir.
No. You see it like a what?
Random distribution.
Random fluctuation, exactly. So that's the data analysis. Those who work in the finance companies, they just looked at the data. You see that it's just a random fluctuation. They said, hey, there is an information there. Their mind can see not just the ring structure. The ring is the second order. They can see even third order correlation, delta k cube or delta k to the power 4, higher order. Okay, they are the higher levels. I cannot see that. Okay, like that. Okay, so these are the heart of physics as well as finance market, as well as condensed matter physics. If you want to do anything in physics, Fourier transform is a deep philosophy. You need to understand it, what it means. When I was selected for TIFR interview for PhD, they just gave me something in the board, and he told me, I have never done it. He said, like, Fourier transform it. And I said, like, I cannot do it because I don't know all this integral and all this thing. Then he started speaking me, what is Fourier transform? He got into the intuition, the interviewer. He is a big shot, Sandeep Trivedi. And he was director of TIFR, and now he retired. Now he's still there. Then, without knowing the mathematics, he took 1 hour. He didn't ask me anything. In the board, with intuition, what does Fourier means? So look at this physical system. Which wavelengths will not become high weight? Which wavelengths will not become low weight? Where you should expect a peak? Karte. I finally, of course, I also have the intuition a little bit. Otherwise, they will not spend time on me. But after 1 hour, I got the Fourier transform, even without knowing the integral and all this thing. And they offered me the PhD. I didn't go, of course, I went to US. But this is what it is. Physics is not just mathematics. You have to understand the Fourier transform, the mathematics and the quantity and what is happening inside. That will be very important in the next 2-3 class. Okay? Yes? Okay. So you are enjoying till now the cosmology course? Yes?
Yes, sir.
Yes. New things you are learning, no? Yes?
Yes, sir.
Hopefully I will be in Pondicherry after the pandemic, because I love Pondicherry. And I have to go also to get my rice cooker and my dress. Last year pandemic I left and I did not go back. So hopefully, when is your, they didn't tell you anything, no? When is it? Okay. So it will be in July or June end. But it will be online, or you will be coming? Even the currency. So all the exams has been online only till now. Okay, very good. So after the end semester, what is your plan? All of you? Jahan, what is your plan?
My plan is to do try for a research, like
Try for
research, type of PhD admissions.
India or abroad?
Wherever.
Other people? Shruti, what is your plan? Huh? Okay. Okay. But you are doing your physics or astrophysics specialization? Physics, but specialization is in astrophysics, yeah? Okay. So you can also give the JEST exam, you know, na? I know. JEST, all the Indian institutes, not only NET, they can take from JEST, isn't it? So Ravi, you got through JEST or NET in IIA?
Net, through net.
From NET, okay. NET interview. Okay. Avinash, what is your plan?
I'm also like looking forward to do research, but I'm trying abroad.
Trying abroad, okay. My 2 students got in abroad, means they were ISA students. They did a project with me, but they had a good GRE score. So you have to have a good GRE score. You know that, no?
Yes.
Yeah. Anything else? Gauri, Shankar?
Yes, sir. Same. Looking for PhD. Yeah. After that.
To prepare jest, there is some questions and solutions of physics, which is little bit above jest standard, but need jest, they can help you. I can give you the references later. You can email me. That helped me, at least in my time. I cracked jest, NET, everything. And they are called problems and solutions in quantum mechanics, in electrodynamics. There are 4 books. They are the question and answers in some problems. They are very helpful. Okay. If you need, you can email me personally. I'll send you the link. You can buy it from Amazon or Flipkart. Okay.
Yes, sir. Thanks.
ठीक है. Then we'll see you Monday. So this is how many class I have taken today? Which number it was? 8. Okay. So not 6. So introduction also part of this 8 class. Okay. So I take 3 or 4 more. Is that okay? For all of you, okay, no? Yeah.
Yes, sir.
If you want to know a little bit more, then we can take 4. If you want to know less, we can take 3. Okay. Yeah. Okay. Good.